Using the ideas of vector fields that I just introduced beforehand, we're now going to go over the proof of Brouwer's fixed point theorem. So let's draw our closed disk X, right? So X is a closed disk, and we are going to let F be the mapping from this closed disk to itself, right? So if I have a point X and I have a point F of X right here, right? So let's make these a little bigger. Then this mapping f of x will take f to f of x, but within this closed disk, right? So then we're going to define a vector field Vx to be all of the vectors that take x to f of x, right? So they kind of like, they show that motion. So at this point, I'm going to try to label these just so we don't forget. So that's x, and this point is f of x. All right, and then this disk is closed, right? Because it contains this outermost line, right? So all these points in this outermost edge are included in this disk. And also, this resembles a simple closed curve, right? So we're going to call this outside edge the simple closed curve C. So that's this outermost edge, okay? And then what we want to do is we want to define another vector field W. W will send, my battery's almost dying. I think we can finish. W sends a point from this outermost closed curve, right, to some arbitrary inward center point, right? And so that is the vector field W, and this is the vector field V, right? So as we move along this closed curve C, and we consider it in respect to W, it's clear that the index will be 1, right? So there's some unmoving or fixed point here at the center, right, that W moves around if we just consider this closed curve C, right? And going back to the idea of vector fields changing, well, I went too far, changing really gradually, how we talked about right here, right? We can continuously deform the vector field V to the vector field W, right? So we can like kind of take this and, you know, like bend it here, and then we can bend it like this and have a vector, and so on, but much more gradually than that, right? And so because this is continuous, and because vector fields kind of just change gradually over time, it's pretty clear that the index of any closed curve that we would have placed in V at any time, or W, would still have the same index, right? So the index of C in respect to W and the index of C in respect to V are the same, right? And because V kind of takes up like this whole interior space, right? And its index is non-zero, right? So we can't have an index that is greater than 0 if we don't have a point to define that index, right? So if I don't have a point, I can't go around it 1 times or 2 times, right? We have to have that critical point in order for the index to be greater than 0. And since the index of C in respect to W and index of C in respect to V are the same, then and V plotted x to f of x, so it showed the entire mapping within this closed disk, that means that there is obviously some point where V takes this, so there's some point C, right, where V maps this point to a 0 vector, right? Or V takes this point to a 0 vector. And therefore, there is a point that F maps to itself. And that is our fixed point. And that is our proof. Thank you very much.